So, good noon, everyone. I am Rahul from IIT Ropar. So, here I am to present my talk in collaboration with Dr. Ajay Beniwal from University of Glasgow. So, my talk will be on room temperature operated Fe2O3 PANI-based sensor, which is eco-friendly and with sub-ppm detectability. So, while moving through the slides, we will see the introduction to the sensors, discuss the importance of ammonia sensing. We will see the sensing parameters that will define the which parameter define the sensing performance of the sensor. Then we will see the fabrication and material characterization of the device, and we see ammonia sensing performance of our developed device and compare with some previous works. Then conclude the presentation. So there are a lot of analytes and the sensors are developed for them, like heavy metal ion sensors, gas sensors, organic and inorganic compound sensors like pH, pressure and flow rate sensor, light sensor, temperature and humidity sensors. So we are generally working on gas and lead sensors, and basically in this presentation we will discuss about NH3 sensors. So why ammonia? So it is well known that the long-term ammonia exposure can lead to life-threatening disease to human. Also, ammonia act as a biomarker. Ammonia in breath can be used as biomarker for the chronic kidney disease. So it is important to detect and monitor the ammonia in environment as well as for biomedical application. However, there are various challenges in ammonia detection, like low concentration, there is lack of low concentration detectability, high temperature required for the detection. They have poor selectivity, and there is non-availability of flexible and eco-friendly type of sensors. So in this work, we have developed flexible, biocompatible room temperature ammonia detection at sub-ppm level. So there are various performance parameters which govern the performance of the sensor. These are response, selectivity, response and recovery time, repeatability, reproducibility, and stability. So response is basically the changes which sensor show when it is exposed to the target analyte. Similarly, selectivity is that parameter if there are various type of gases present in the environment. So our target gas sensor should be selective for the target analyte. So the maximum response it should show for the target analyte. So selectivity defines that parameter. Similarly, it should behave quickly so that we can detect easily, and the repeatability, reproducibility, and stability are the important parameter for the practical applications. So these are the parameters which will define our sensor. So we have used paper substrate above which we have printed electrode using carbon graphening using screen printing method. So after printing electrode, we have annealed it for 60 degrees Celsius at 60 degrees Celsius overnight. Then we have electrospin the pani above that substrate. After electrospinning the pani, we have drop casted iron chloride solution and annealed to develop Fe2O3 nanoparticle of that. So our sensor became ready, and after that we have characterized for the gas sensing in a controlled environmental chamber using keysight source meter. In figure A, we can see the image of our original optical image of our original sensor. So you can see the green part is that electrospin pani, and electrode is clearly visible. Figure B and C are the XRD and FTIR analysis, which confirms the presence of PANI as well as Fe2O3 decoration over the substrate. So figure A and B, we can see the decoration PANI, and the dotted circle represent the Fe2O3 nanoparticle over that PANI surface. And we have studied the IV characteristic of the sensor, and it is showing linear behavior. Ammonia sensing performance is studied for the 0.5 to 50 ppm of ammonia, and we can see that 0.5 ppm, such a low level of ammonia is also showing response, that we can see the resistance is changing from 3.35 kilo ohm to 3.4 kilo ohm approximately. So, and the figure B, in figure B, we can see the corresponding response of the sensor. And the sensor response generally lies between nearly 2% to 9% for the 0.5 to 50 ppm of ammonia. And figure C is the zoomed version of that 0.5 ppm of ammonia. And here we can see how we have calculated the response and recovery time. Here response time is nearly about 950 seconds and recovery is 250 seconds. It is generally the 90% change while moving from baseline to the saturation level of that inlet. Similarly, for recovery time, the declinement from that saturation to 10% of the total change. Similarly, the selectivity of the analyte is also studied with respect to carbon dioxide, carbon monoxide, NO2, and SO2. These are some major analyte present along with that NH3 in the environment. And we can see there are quite good selectivity for NH3 with respect to these other analyte present in the environment. So we have compared our study with some other work that is PANI, other work of PANI and Fe2O3, and we have seen that our sensor is both flexible as well as degradable compared to other. Other things are that most of the sensors are working at room temperature and only have WO3 and Fe2O3 nanorod showing its sensitivity at 375 degrees Celsius. Otherwise, most of them are showing well response, but they are not biocompatible and biodegradable. So the concluding point is that we have developed Fe2O3 and PANI-based sensor where we have achieved selectivity for ammonia, and the sensor is on paper-based substrate, which is biodegradable and biocompatible. And the material analysis shows that XRD and FDR shows that formation of composite of PANI and Fe2O3 decoration over that. And the sensing response lies between 2% to 9% for 0.5 ppm to 50 ppm. And it is showing good selectivity in compared to CO2, CO, NO2, and SO2 with quite good response and recovery time. So it can be useful in healthcare application and environmental modeling and can further be improved with further modulating the PANI and Fe2O3 substrate. Thank you.